Today we're going to talk about diagonalizability. In order to do so, let's first review some concepts of eigenvalues and eigenvectors. We'll explain how we can compute the eigenvalues and eigenvectors of a linear transformation T. Let's say that V is a finite dimensional vector space and we have a basis beta. Let's denote A as the matrix representation of some linear transformation T going from our vector space V to itself. Our first statement says that T is diagonalizable if and only if there exists an ordered basis beta consisting of eigenvectors V sub j of T. If this is the case, then our matrix representation A is a diagonal matrix, and the elements on the diagonal are the eigenvalues associated to these eigenvectors. Our second statement says that the following four are equivalent for any scalar lambda. Lambda is an eigenvalue for our linear transformation T. Lambda is an eigenvalue for our matrix representation A. The determinant of the n by n matrix A minus lambda I sub n is 0. And finally, there exists a non-zero vector, lowercase v, that lies in the null space of the linear transformation T minus lambda IV. Our third statement goes as follows. For any variable t, let's define f of t as the determinant of the n by n matrix A minus t times the identity matrix I sub n. This is a polynomial of degree n, which is independent of the choice of basis beta. In particular, our linear transformation T has at most n distinct eigenvalues lambda. Last time we saw how to use this result to compute the eigenvalues of a given linear transformation. We'll explain this in 4 steps. First, let's choose a basis beta of our vector space V. Second, we'll compute the n by n matrix A, which is the matrix representation of our transformation T. Third, we'll compute that degree n polynomial, which is the determinant of the matrix A minus t times I sub n. And finally, we'll compute the roots lambda of the equation f of lambda equals 0. That is, the roots lambda of this polynomial f of t are just the eigenvalues of t. This polynomial f of t is called the characteristic polynomial of the linear transformation T. We'll see later how to use all of this to compute the eigenvectors lowercase v corresponding to this eigenvalue. Today, let's go over a few examples to understand how this algorithm actually helps us. Let's assume that V is R2, the real plane. First, let's consider the linear transformation that is just the identity transformation. That is, I sub v is just that map that takes a vector x to itself. Upon choosing the standard basis, where e1 is the vector 1, 0, and e2 is the vector 0, 1, then we see that the matrix representation of this identity map is just the identity matrix, 1, 0, 0, 1. In particular, it has characteristic polynomial f of t, which you can see here after some algebra. It's just parentheses t minus 1 squared. This means that our identity map I sub v has just one eigenvalue, namely lambda sub 1 equals 1. Again, let's consider V as R2 is the real plane, but now let's consider that linear transformation L sub A, which is left multiplication by A, corresponding to the following matrix. Capital A is 1, 1, 1, 1. In this case, we have the polynomial, the characteristic polynomial, which is the determinant of A minus t times I sub 2. Here we're computing the determinant of the matrix 1 minus t, 1, 1, and 1 minus t. After some algebra, we find that this characteristic polynomial factors as t times t minus 2. This means that our transformation, L sub A, has two eigenvalues, namely lambda 1 equals 0 and lambda 2 equals 2. As our third and final example, let's consider that linear transformation which is reflection about the line y equals mx. We've seen before that if we choose our bases in terms of v1 and v2, as you see here on your screen, then this linear transformation sends these vectors in a rather simple way. T of v1 is plus v1, and T of v2 is negative v2. You may recall that v1 is in the direction of the line y equals mx, whereas v2 is in the direction perpendicular to this line. Upon choosing gamma to be the standard basis, as we've done all along, we have the following matrices. First, capital A is just the matrix representation of our transformation T with respect to the standard basis. Here, all that we're doing is looking at the matrix where T is A times X. Next, let's define Q as the change of coordinate matrix. Here, we're simply replacing the columns of Q as the vectors v1 and v2. Hence, we have a new matrix, A prime, which is Q inverse AQ, which we can write as the matrix representation of T with respect to this new basis, beta. Here, just by realizing that T of v1 is positive v1 and T of v2 is negative v2, we see that A prime is the diagonal matrix corresponding to 1, 0, 0, and minus 1. Now we'd like to compute the characteristic polynomial. We could compute the determinant of A minus TI2, but this would be a lot of work. Instead, let's recall that our theorem said that the characteristic polynomial is independent of the choice of bases. So instead of computing the characteristic polynomial while choosing the basis gamma, which would give us back the matrix A, we will instead compute using the basis beta, which will give us the matrix A prime. For beta, that is for A prime, our matrix is much, much simpler. And we see now that we're just computing the determinant of 1 minus t, 0, 0, negative 1 minus t. Once we multiply this out, we see that it's simply the polynomial t minus 1 times t plus 1. And hence, our linear transformation t has just two eigenvalues, namely lambda 1 equals plus 1 and lambda 2 equals minus 1. Let's go a little bit further into this idea of diagonalizability. First, we'll recall our definitions. We'll say that a linear transformation T from a vector space V to itself is diagonalizable if there exists an ordered basis such that the matrix representation of T from beta to beta is a diagonal matrix. That is, if we can write the matrix representation corresponding to lambda 1, lambda 2, so on, through lambda n along the main diagonal. This is equivalent to saying that we can find a basis beta consisting of the vectors v1, v2 through v sub n, such that t applied to each v sub j is a scalar multiple, lambda j, times v sub j. A square matrix A is said to be diagonalizable if the linear transformation left multiplication by A is diagonalizable. Here we have the main result for the day. Let's say that T is a linear transformation from a vector space V to itself. For the first statement, assume that T has k distinct eigenvalues, where of course k is less than or equal to n. If S is a set consisting of k non-zero vectors, v1, v2 through v sub k, such that T applied to each v sub j is lambda j times v sub j, then S is a linearly independent set. In particular, if k equals n, then T will have n distinct eigenvalues. In this case, T is diagonalizable. Before we go over the proof of this result, let's make a couple of remarks. Let's say for the moment that k does indeed equal n. This means that T has n distinct eigenvalues. Then we've seen that a collection, beta, consisting of v1 through v sub n of eigenvectors is a basis. That's just the restatement of the previous result. For example, let's go over what we just said a few minutes ago. Let's say that t is a reflection about the line y equals mx. We've already seen that this has two distinct eigenvalues, namely lambda 1 equals plus 1 and lambda 2 equals minus 1. In particular, the eigenvectors associated to this transformation t must form a basis for our real plane R2. However, let's say what if k does not equal n, but t still has k distinct eigenvalues? It may still be the case that t is diagonalizable and that its eigenvectors still form a basis. For example, let's go back to the identity map. We've seen that this only has one eigenvalue, namely lambda sub 1 equals 1. However, we've also seen that this has two eigenvectors, namely e sub 1 is 1, 0, and e sub 2 equals 0, 1. This means that our transformation, I sub v, actually is diagonalizable because its matrix representation is a diagonal matrix. So again, it may be the case that t has k distinct eigenvalues with k not equal to n, but t still be a diagonalizable linear transformation. Let's go ahead and prove the theorem. We're going to prove the very first statement by induction. So we'd like to consider the following proposition as a function of an integer k. Let's say that t has k distinct eigenvalues, lambda 1 through lambda sub k. If S is a collection of k non-zero vectors, v sub 1 through v sub k, such that t applied to each v sub j is lambda j times v sub j, then S must be a linearly independent set. We'll start by establishing the base case. Proposition P of 1 is true because when k equals 1, our set S will consist of just one non-zero vector. It's easy to see that S must be a linearly independent set. Now let's assume the inductive hypothesis, that is that proposition P of k sub 0 is true. Let's work on the inductive step. Let's assume that our linear transformation T has k0 plus 1 distinct eigenvalues, lambda 1, lambda 2, through lambda sub k0 plus 1. Let's consider a collection S of k0 plus 1 non-zero vectors such that t applied to each v sub j in the set equals lambda j times v sub j. We're going to consider an expression of the zero vector where we have a linear combination a1 times b1 plus a2 times b2 plus a sub k0 plus 1 times v sub k0 plus 1 equals the zero vector in our vector space V. In order to show that S is a linearly independent set, we're going to show that each of our scalars, a0, a1, a2, through a sub k0 plus 1, must each be equal to 0. To this end, let's take this expression for the zero vector and let's apply the operator t minus lambda k0 plus 1 iv to both sides. Of course, when we apply t to each vector v sub j, we just get lambda j times v sub j. When we apply I sub v to each vector v sub j, we just get v sub j. So when we apply this difference, t minus lambda k0 plus 1 times iv, we really get the same sum as before, but we multiply each v sub j times the factor lambda sub j minus lambda k0 plus 1. Of course, when j equals k0 plus 1, then we actually see that this operator applied to that vector is just the zero vector. So really we've eliminated everything except for the first k0 vectors. Now let's consider the set S prime defined in terms of w sub j, which is this scalar multiple, lambda j minus lambda k0 plus 1 times v sub j. Since the eigenvalues lambda sub j are distinct, each w sub j is a non-zero vector. Again, v sub j is a non-zero vector, and the scalar lambda j minus lambda k0 plus 1 does not equal to 0. But you can also check that t applied to each w sub j is just lambda j times each w sub j. By the inductive hypothesis now, we see that S prime must be a linearly independent set. So since we have a sum at the top of your screen of the elements from S prime equals to the 0 vector, this cannot be a non-trivial expression of the 0 vector. So each scalar, a1, a2 through a sub k0, must be 0. But let's go back to the identity that we had on the previous screen. Here, recall that we had a sum involving the 0 vector, a1 v1 plus so on and so forth, a k0 plus 1, v k0 plus 1 equals the 0 vector. But since the first k0 scalars, a1, a2 through a k0, must be 0, we see that we must have the final scalar, a k0 plus 1, to be 0 as well. Indeed, recall that vk0 plus 1 is not the 0 vector. So this proves that our set S is indeed a linearly independent set, showing the proposition p k0 plus 1 is true. This means that the proposition p of k must be true for every positive integer k. So let's go ahead and show the second statement. Let's assume that our linear transformation T has n distinct eigenvalues, lambda 1 through lambda sub k. According to the statement, we know that we can find n non-zero vectors in beta such that T of v sub j is lambda j v sub j. But we know that beta is a linearly independent set, and the size of this set is the dimension of v. So this means that beta must be a basis for v. But now we have a basis consisting of eigenvectors for our linear transformation T. This means that T must be diagonalizable. Thanks very much for watching.